Hello there, everybody. Welcome to my presentation. Good afternoon, or depending on where you are, good morning or good evening. I'm going to be doing my paper presentation on programming in large versus programming in the small, and I'm very excited to be presenting to you and also to meeting everyone virtually through all these other presentations. So let's get right into it. So here today, I'm going to give you an entire summary of the paper. I'm going to give you an impact on the field, critiques of the paper, future work, and then I'm going to summarize off with a conclusion. So let's start off with a summary of the paper. So Programming in the Small versus Programming in the Large was written in 1976 by Frank de Rimmer and Hans H. Kranz. I put a picture of them here just because of the hairstyles from the 70s, which my hairstyle is mimicking these days. So it's a very seminal paper based around the detailing of different scales of programming. So they say that most programmers are getting lost in the trees, so to speak, and doing programming in the small and can't see the entire forest most times. So they make the distinction that creating modules, which is programming in the small, is very different from creating the entire system itself, which is programming in the large. And as such, they deserve different paradigms or abstractions and, in essence, programming languages. So they make the distinction between languages for programming in the small, or LPSs, and module interconnection languages, or MILs. So in the paper itself, they go on to make their own version of a module interconnection, MIL75 or MIL75, and it's their solution for programming in the large. They provide a rigorous structure to how to document your system instead of having your system documentation between comments and modules and then external documentation and all that. The actual module interconnection language itself provides a way that you document the structure through this actual programming of the MIL itself. So as pictured in figure 1 above, they give an example of a theorem proving program, and this has a couple different aspects that you can see to it right off the bat. So there is nodes, which are the ones with titles in them, and anywhere you see one of these circular or ovular nodes with a square attached to it, that's a module, and that's the actual physical LPS module. And then the nodes are connected themselves by the system tree architecture, which is a solid tree, the solid black line right there. And then you're also going to see accessibility links in between them. That's a form of Parnas information hiding, which says which nodes can access which informations. And they have a very, I won't say complicated, but a formal structure on how to do that. And then they also delineate where used resources from other nodes comes from. So making sure that they know what all the other modules are accessing at the same time. And if you've ever worked on a large system before, you know that when you're working with distinct modules, that this can get very messy very quickly. So this idea of having a larger or different scheme for programming these modules together sounds really exciting. And they get into that in the paper on why MIL75 is a really exciting technique. So speaking about that, let's talk about the impact of the field itself. So looking on Google Scholar, Frank de Rimmer and Hans H. Kranz for this paper were cited over 800 times as of April of 2021. So a couple of references that I looked into in my limited research saw them, coining the term, of course, and the idea of these two different programming scales. They also said in another reference that MILs themselves have gone on and had a little bit more worked on in them. Not MIL75. I couldn't find any grandchildren of MIL75 itself, but there was modular connection languages made for MESA and Ada, and some of these systems went on to do software construction, version control, and dynamic configurations. So in an abstract way, this idea is still around today in the idea that we know that making small programs versus large programs are very different. And speaking of which, there's another term that most people are probably more familiar with, and that is Ousterhout's dichotomy. So if you've ever heard the term scripting language, Ousterhout, much later than Programming Large versus Programming Small came up with this dichotomy where he said that system programs or system programming languages are responsible for making components. So that would be your C and C++ languages that make the very small modules of the actual language themselves together. And then there are scripting languages that actually are responsible for gluing these components together. Some examples are Python or any other high-level language that isn't necessarily dealing with much more low-level details. If these languages, he said that they're generally distinguished by their typing, having complex or non-complex data structures, and whether they're compiled versus interpreted. And if all this dichotomy seems a little bit arbitrary, that's because it definitely is, and there's been many critics of Ousterhout's dichotomy. But I just wanted to show how programming large versus programming small went on to influence these other ideas, and these ideas are definitely found. So that's why this is a seminal paper itself. So now, saying about how the paper ideas are good, let's go on to some of my personal critiques of the paper. And one of the most glaring ones was just how little comparison having a module interconnection language to not having a module interconnection language was. So they don't do any kind of qualitative or quantitative comparison. They start off with this theorem proving program, which was made by Professor Sharon Sickle at UC California, Santa Cruz. And before he had made this using LPSs, and they state that they even improve it and then restructure it using their own system for MIL75. But then they don't go on to compare it in any sort of way to say what process was better. They just say that programming at large is definitely a good scheme that we should go with. So these ideas that they put in the paper are really great, but they're not really backed by any sort of evidence that you might want in a rigorous scientific paper. And you may say, well, Brendan, but maybe this is different the way they wrote back then. But any kind of science paper, I think, should have some sort of evidence in comparing to say, okay, it's actually better because X. And then some other problems that I had it could mostly be me as a beginner, but some things that I had to read a couple times that I had a little gripes with. The acronyms, some of them, such as LPSs, Languages Programming in the Small, bit of a mouthful. Might want to go to marketing to rephrase that acronym itself. The other one was this figure that I show in this diagram above, figure 1. So figure 1A, the clauses in Theorem Prover, it says to see figure 1B and figure 5. So it first was hard to tell that figures 1B and figure 5 are subtrees of this figure. And that wasn't very clear. I don't know why they didn't put it in one figure or in separate figures altogether. Figure 5 is on a different page. A little bit of a confusing to actually try and resolve how this Theorem Prover works and see the entire tree in one place. And the actual semantics section of MIL75. So they cover a pretty big section of the paper. It's only a 7-page paper, so very short but good read. And 2 pages of those are spent on how MIL75 works and the semantics of it. But a lot of that is formalism that is a little difficult for beginners to read if they're not familiar with programming languages, formalism, and as well as have a good understanding of discrete math, which I'm a little bit of a beginner, so it was a little bit more tricky and it took me some more time to read that. Now let's talk about where I would bring the paper in the future if I were to work on it. So the biggest outstanding critique is then what I'd want to work on. So how much better is a modular interconnection language with an LPS than just standalone programming with these LPS languages, especially ones that we have today that might have some of these language features that do for programming at large. So I would do a case study between a fairly large program, one you could have one where you're just doing an LPS language and one that you have an explicit modular interconnection language plus the LPS itself, and then compare them in some sort of way. Use metrics of some kind. These metrics aren't perfect, but lines of code, hours of work, hours of debugging, and then qualitative feedback from the actual developers themselves to see how much more rigorous this structured programming actually is itself. Ideally, if we could use a case study with MIL75, that would be great, but MIL75 doesn't really seem to be around in any sort of way, so maybe a more modern modular connection language would be great to use. Then my other big outstanding question and room for future work is just how big is large. So I show this picture of a building. So it's really easy to imagine if you're creating a modeling system using model-driven engineering and creating a tool that this is going to be a pretty large project to have to deal with, say, a building. So that would probably be programming large. And if you're just creating a single module, that's probably programming the small. But where in between is this continuum that you might want to start using a modular interconnection language? When is it economical to start using a modular interconnection language over just a language for programming the small? So is there any rough estimates that we could do using, even if it's a bad metric, but lines of code to be able to see when a programming language should start using a modular interconnection language? This is just some of the questions that I would like to get answered with some future work, just to add a little bit more specificity to these two different paradigms, because I think it's important. So, in conclusion, this paper, Programming the Large versus Programming the Small by Frank DeRimmer and Hans Cron, they make the distinction between these two different scales of programming. One, you have modules, which should be using language of programming the small, but for any bigger systems comprised of modules, you should be really using a different system or a modular interconnection language to do this structured sort of programming. These ideas are still extremely relevant and used all throughout programming today in software engineering and computer science to be able to work on different systems at different scale, but more in their abstract form. I would still definitely recommend you read this paper. It's extremely short, really easy to read, except for maybe the formalism section. So maybe skip some of the parts about MIL-75 and the technology itself and focus on the ideas that they present, because I still think it's a really great and relevant paper for today. So I've got a couple of different sets of references throughout, but that has been my presentation. Thank you very much for listening. Really appreciate it. Hope you enjoy the rest of the presentations, and have a good afternoon, good evening, or good night, depending who you are. Thanks for listening.